I love math. Do you? Well, if you do, you should live by the math commandment that states, Thou shalt do unto one side of the equation what thou doest to the other.
Hey students, let's go over lesson 1.8, solving linear nonlinear systems. Let's go to dark mode. Let's take a look at our directions. Questions 1 and 2, we need to solve the system by using substitution. Go ahead and try that. Kobe gets tired, he has to go out, he has to be substituted. Calls for a sub. Go ahead and try those questions, and then question number 1, you're going to recognize that the second equation is already solved for. What I highlighted here in pink. And what that means is you see the variable y is by itself, it says y equals. Well, I'm going to put that into the first equation. We're going to do a substitution. 3x plus 2 times 2x minus 1. So basically, instead of writing y, I wrote 2x minus 1. And here we're just going to solve, so I'm going to distribute. 4x minus 2 equals 12. Combine like terms, 7x. Add 2, you'll have 14. Divide by 7, x is equal to 2. Okay, now to solve for y, you can pick any of those equations, the first or second one. I think the second one's more efficient because it's already solved for in terms of y. So if I put x equals 2 into the equation here, y equals 2 times 2 minus 1. So that becomes 4 minus 1, which is 3. So our order pair is 2, 3. If I make a quick visual to help you understand this, draw my coordinate plane here. If I take the first equation, which is called standard form of linear equations, and I make it into slope-intercept form. So it says y equals, I have negative 3 halves plus 6. I have a negative slope, goes through 6. Super quick sketch here. And then y equals 2x minus 1, so y-intercept of negative 1, positive slope of 2. And the whole point here I'm trying to show you guys is that the intersection of the linear equations is 2, 3. Here in orange. In question number 2, we're going to have to do a little bit more work. You'll notice that both the equations, the variables are not solved for. It doesn't say x equals or y equals. That's how you know to use substitution. So what I'm going to do here, you can choose your own adventure. I'm going to add 2y to both sides on the second equation. X equals 8 plus 2y. Now that I have x by itself, I can put that back into the first equation. Do not put it into the second equation because that's the one we just worked with. So instead of writing 2x plus y, I'm now writing 2 times my substitution here, 8 plus 2y. Plus y equals 6. Now we can just solve for y here. I have 16 plus 4y plus y equals 6. And then we're just going to solve here. 5y equals negative 10, and y equals negative 2. We're going to put that into any equation you want. I'm going to put it into this one here because it is already solved for in terms of x. 8 plus 2 times negative 2, so that becomes 8 minus 4, and that becomes 4. X equals 4. So if I just draw myself a quick sketch, I'm just trying to show you guys a visual of what we're doing here. We have two linear equations. They're in standard form. If you change them in the slope-intercept form, super easy to graph. If I subtract 8 and then divide by 2, I'll get 1/2 x minus 4. So go down to minus 4. And 1/2 is positive, so from left to right it's going up. And over here on this equation, if I subtract 2x, then I have that in slope-intercept form, so positive 6. Negative slope, so it's going down. And I kind of messed up here. To fix this, I'm going to erase the x-axis. And let's move it up. And I'm doing this because the intersection is 4, -2. So notice my drawing is not drawn to scale. Point of intersection here, 4, -2. Let's go ahead and try solve each system by elimination. This method is a little bit different, and what you're trying to do is when you add the two equations together, you're trying to get 0. So I'm going to multiply the first one by 2, and if I do that, I get 10x plus 4y, and you also need to multiply the other side, so you get -26. Let's go ahead and add these together. You're going to get 19x, and this is what we wanted here. We wanted those to add to 0. Therefore, it's eliminated. -57. You see 19 and x, so the opposite is division. So divided by 19, x equals -3. There is an answer. Now I need to solve for y. You can pick any equation. You can pick the first one, second one. I'm going to pick the first one because the numbers are a little bit smaller. We're going to put in x equals -3 here. And I get -15 plus 2y equals -13. Let's add 15 to both sides. 2y equals 2. Divided by 2, y equals 1. Okay, I'm not going to give you a super accurate graph here. I'm just going to want to show you a solution here. So I already know that the order pair is -3, left 3, up 1. That's where the two graphs will intersect. So the blue and orange graphs here, I'm just kind of making them up, but I'm trying to show you that they intersect there at -3, 1. That's why that's the solution. Question number 4, choose your own adventure. You can eliminate the x's or y's. I think I'm just going to eliminate the y's. So if I multiply this equation by 3, let's go ahead and multiply it. 9x minus 3y equals -18. Let me go ahead and copy down the first equation. So here you'll notice I've eliminated the y's. That becomes 0y, so you don't write 0. And you have -16. And you get x equals -1. You can put x equals -1 to any equation. I picked the second one. I think the number's a little bit smaller, so x equals -1 here. -3 minus y equals -6. And we'll get y equals +3. So the intersection is -1, 3. And just want to show you that the quick intersection of these two graphs is left 1, up 3. Alright, let's go over our standards for mathematical content. AREI 11. Explain why the coordinates of the points where the graphs of the equations y equals f of x and y equals g of x, their intersection. Their intersection are solutions. Where they cross, they are solutions. You know, where two streets cross together, that's called an intersection. Well, that's a solution for systems. And you can use this by using technology to graph, which we'll do later. We're not going to make tables in this lesson. But you also notice linear and polynomials and different ones. But that second one there, graphing. Standards for mathematical practice. How can I use these practices? Well, math practice 1, reason abstractly and quantitatively. You can make a plan to find a solution to a problem by explaining its meaning and looking for entry points to its solutions. And mathematical practice 4, model with mathematics. I can model problems, the functions, and use them to better understand those problems. Alright, let's listen to this robotic voice man for our lunch.
The European Space Agency has been running tests to see how nets can be used in orbit to collect space debris, such as detached rocket parts or satellites that are out of commission. To test the behavior of nets before trying the process in space, he and others at the ESA tested shooting nets in straight lines out of aircraft flying in parabolic arcs, which models the weightlessness experienced by objects in orbit. You can use a linear quadratic system to predict how the net should be deployed to catch debris.
Thank you, Mr. Robotic Voice. Okay, vocab word. Here we have one called quadratic relations. It's just equations of parabolas with horizontal axes for symmetry that are not functions. They're just expressions. They have no equal sign in it. Okay, this next part is like a game or a puzzle. Let's check it out. Hey math students, got a little puzzle here for you. This is the introduction of solving systems, and just as a quick reminder, how did you solve linear systems? You did it by elimination, graphing, and we're going to do substitution and replace. But here's my little puzzles. Can you draw the pictures that kind of show, for example, in this column in blue there, it's linear and a linear. Can you draw me two linear graphs that have no solutions or no intersections? Over here, can you show me a linear and a quadratic that have, you know, in this middle column here, one solution or one, and then the quadratic, can you show me that it has infinite amount of solutions or intersections? Press pause and then I'll give you a hint. Alright, here's hint number 1. A linear and linear has 0 solutions. So here's my graph. Zoom in over here. This is a linear. Question. Do the lines, two lines, intersect? No. So there is no solution there. Let's try a linear and quadratic that has one solution. We could draw a quadratic here. And let's say that goes this way. So then our intersection, the one solution would be that red dot. And let's go ahead and try a quadratic and a quadratic. Did orange, let's try orange. And we're trying to get infinite amount of solutions. So here's my one graph. Here's the second one. It's gonna go fast. Whoa, why is that the case, right? Because the point of intersections are every single point. There's a, I can draw dots all day long. about the number of solutions, right? Looks like it's sick. So, alright, you finish that up, press pause, and then I'll show you guys the rest of those solutions. Alright, so the graphical one solution for linear-linear is just going to be a intersect, right? Alright, you guys want to hear my story? Okay, you gotta hear my story. This is like world famous. This is like the most famous story sometimes my students love, okay? There's two lines there, and the two lines come into class, and I make them sit next to each other, and they look at each other and say, hey, do you want to hang out and go on a date? Or, you know, and they're like, nah, we're never going to go on a date. That's no solutions. Their love lives are parallel. I sit next to another two students together, the blue and the green, and they look at each other like, whoa. Looking at each other, and then they decide to go on one little hangout, one little date. Come back to class the next day and like, let's do it again. Oh no, sorry. And then the last one, because I really like this one. Sit next to each other and whoa, they're on top of each other. Why? They're like one, right? Their love lives are infinite. Their commonalities are infinite. Do you like that? It's better. I'd use pencils and stuff like that. But let's do linear and quadratic. Let's do something different, right? Whoa. Totally missed it, right? No intersection, no dates, no solutions to that one. Okay, how do you get an infinite? Okay, this one's going to be impossible, but so there is no infinite. But there is one I missed. There's actually two solutions. Can you think of it? Yeah, you just have a, and somehow it goes this way, right? Then your two solutions are going to be there and there, okay? And let's do the quadratic and quadratic. Can we have it where it has no solutions? Can you think of something? How about this? Right? Okay, how about a graph that has quadratic that has one solution? Okay, this one's going to be a tough one. Let's see if we get it. There's one. How do you get the second one? Whoa! Take a look right there. Bam! One solution. And then there's the infinite solutions. Okay, so that's introduction of solving of systems of equations, linear, 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 quadratic, 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 and then we're going to be focusing on the substitution method. Alright, see you guys. Hey guys, I wanted to go over some steps of solving quadratic systems. Steps, and we're using the substitution method. Number one, use the substitution method when both when they're both set equal to y. So you might get an equation like something like this: y equals x squared minus 1 and y equals x plus 1. So you notice that both of those are set equal to y. Number two, set it equal to 0. So in that case, you might have something like x plus y equals x squared minus 1, right? You are taking this right one and putting it for every y variable here. So instead of writing y, you're going to write x plus 1. And then you're just going to move all of this to the other side. That's what it means there by set equal to 0. Number three, you would just solve that quadratic equation. So you would have 0 equals x squared minus x minus 2. And then you can use the discriminant. How many solutions are there? Well, if you take this, the discriminant is inside the quadratic formula. So we already know that ax squared plus bx minus c. So I'm just doing this example right here. You have 1, negative 1, and negative 2. So if you put that in, you're going to have a negative 1 squared minus 4 times a value, which is 1, and c value is negative 2. So in our example here, you would get 1
negative 4 times 1 is negative 4, negative 4 times negative 2 is positive 8. So then our answer is 9. Now, you'll recognize that 9 is greater than 0, so you get 2 solutions in ours. Use x to get y. So we would have to solve this one over here. Let's go ahead and solve it. So I'm going to factor it. A times c is negative 2, b value is negative 1. So my two numbers, 2 and 1, negative 2 and positive 1. And so I have this. And then if you solve those, we're still trying to get x right there, right? So zero product rule, set it equal to 0. And just quickly solve that. X equals 2, x equals negative 1. Okay? And then step number 5, use x to get the y order pair. So go back up, and we're going to put that into our y variable. So in my example, I have, change colors here, y equals x plus 1 is probably the easiest one. I'm going to do that twice. Y equals x plus 1, y equals x plus 1, and we're just going to put that in for the variable x. Does that make sense? So then I have y equals 2 plus 1, which is 3. And y equals negative 1 plus 1, which is 0. So the last step we said was we're using x to get an order pair, and sorry, our order pair is 2, 3, and negative 1, 0. And you can graph that to verify those are your solutions. Let's quickly graph that. So y equals x squared minus 1. That's a quadratic, and it's shifted up 1 unit, and graph looks like that. And then x, let's graph our x plus 1. Again is, whoops, that one shifted down. Because it's negative 1 through c value. And then the y equals x plus 1, let me graph that one. Something like this, right? And if we graph our solutions, which are 2, 3, so something like this. And negative, that should probably have been right there, negative 1, 0. Alright, so those are our steps in solving quadratic systems using our substitution method, and then I used graphing to double check.
Mathematics includes the study of quantity, structure, space, and change. Math can be so complex it could be considered strange. So strange equations can be rearranged. Don't even get me started on fractions. To multiply them is going to take a lot of action. But math can be simple. All it takes is practice. Your brain is like a muscle. Make sure it's active.